me if you're confused, but I don't. I would start by looking at the odd and stripping that down. So you could call it cosine squared cosine x dx. This will later serve to be your du, which implies that all the other stuff will be the u. And if du is cosine, then the u probably needs to be all signage. So I would replace the cosine squared with 1 minus sine squared to get an integral of quantity sine squared minus sine to the fourth of x cosine of x dx, so that u sub goes well. Let u equal sine. Therefore, du is cosine. So did you get something like 1/3 sine cubed plus minus rather 1/5 sine to the fifth plus c?
Yes.
Yeah. Cool. All right. How about this bad boy? Where did you place your origin? The picture does not communicate where the origin goes, so you need to communicate it. Put the origin at the lower left? Okay.
Yes.
Cool. Let's go there. When I calculate the force, I'm really calculating the force on each of these slices and accumulating it all because they all have different depths. They all have different forces on each of those slices. So it's more like rho, depth, area. 9,800 for your depth. What'd you say? 10 minus y for the area of each of those little thin slices. 10 dy from 0 to 10 units. Newtons. Okay. Now then, this is going to lead into today's, but be a little bit different here. So today we're talking about, instead of getting fluid in a container and how much force the fluid is pressing against the side with, it's more like how much work would be required to empty the fluid. You can actually do this without even fluids, but we'll talk about it differently later. All right. I would like you to have a basic understanding of not just the equation, but why the variables are what they are. So I used to actually do this in a demonstration. I had 3 students race to see who could empty the container first, but then I had an allergy issue, and so it didn't go well. So I was scared after that. But consider this normal person. I'll call it Corey. Okay? This next person, I'll call her Emma, is trying to empty her container, but she has a really, really, really long straw. Will she do more work than Corey or less? More, all right. This person, I'll call her Harper, is instead of sucking out water from a container, she's sucking out mud. Or maybe ice, a malt or a smoothie or something would be better. Or mud, whatever. Will Harper do more work or less work than I, who am sucking out water from the container? More, okay. What about here, Camille, who is the same kind of straw length, and the front face of the container is the same, yet the back edge of her container goes out much further. Will she be doing more work or less than Corey? More. All right. This is meant to communicate the variables at hand, other than obviously the people. The person is a variable as well, but we're going to ignore that. The variables are, first of all, this. What is the variable here? The length of the distance which you have to pump the fluid. How far do you have to move that fluid? What about the variable at work here? Yeah, the weight density. Or let's just focus. Okay? The more density will affect. And what about this? They have the same area. What's the difference? It's volume. The volume you have to move obviously will affect it. In terms of math, and getting you some vocabulary here, is this a the amount of work related to distance, is that a direct relationship, which is to say as one grows, the other grows? Or is it an inverse relationship, as one grows, the other shrinks? Or a negative relationship? Direct, yeah. Distance relates directly to work. The more distance, the more work. What about density? The more density, the more work? Is that a direct relationship? It is. What about volume? The more volume, the more work? Yes. They're all direct relationship. We call that then joint variation, which is to say work will be some product of distance, density, and volume. All right. The why then this becomes a calculus problem is because one of those is different at lots of different places. If I were to look at, I guess I imported that from some other slide. All right. If I were to look at each of these little slices here that I have to move, the volume of this little slice is the same as the volume of this little slice. And the density is the same, but the distance, am I not going to have to move this slice more than I'm going to have to move that slice further, right? And so that's what makes it a calculus problem. The distance of each slice varies continuously. That means then that it's going to vary with y. Distance will vary with y, and I'm going to integrate with respect to y, a little bit like we did force. Okay? Well then, let's talk about what a problem looks like this, but it'll generally be something like work will equal distance, what else? Oh, weight density will be out here, and volume, and dy will be part of the volume. You will see. All right, let's get into it here. So imagine you have a rectangular prism with base 8 by 6 and a height of 10 centimeters filled with water. The weight density of water, at least in meters, is newtons per cubic meter. So that's unfortunate. We're going to have to do a little unit work, but that's okay. I think you can work with decimals just fine. Let's place the origin. The bottom is 8 by 6, and it actually doesn't matter if you go 6 on the front and 8 back here or vice versa, but I'm going to go 8 centimeters is how many meters? 0.08 meters. This base then is going to go back 0.06 meters to give the base of the rectangle as a whole. And the height is 10 centimeters or 0.1 meters. Okay. Read carefully, however, it's only half filled. So as far as where the fluid is, it's actually at 0.05 is the top edge of the fluid itself. The top half of the container is empty. So far, so good. All right. Now I'm removing slices somehow here. I have some kind of pump apparatus that's pulling out slices and bringing them to the top edge of the container. Pulling them to the surface of the fluid and then letting them go is not going to do anything. To get the fluid out, I need to pull it out and over the top edge of the container. That then is going to be a little bit of a difference. Let's talk about a few of the differences. First of all, this matters for work. This, how far back you went, it matters for work now because it's going to affect how much volume I have. It didn't when we did force. Because regardless of how far back the container went, the force on the front face was still the same regardless of how far. This here, this also matters. Now, for work, we care about the top of the container. Not the surface of the fluid like in force. when we did force, how deep a slice is didn't have anything to do with how big the container was. It just meant where's the surface of the water. But for work, we care about getting it to the top edge of the container itself. So there will be some differences here, and there's danger in getting the two different types of problems confused. If I pull the weight density out front, then I'm going to focus inside distance times volume. I will always start the problem by doing the basic formula. The more I write it, the more you remember, right? If you write it every time, it'll gradually get in your brain quicker. So if the weight density is 9,800, then let's talk distance. Say I was moving this slice at 0.02. How far would I have to move it to get it to the top of the container? 0.08, okay? Now, surely then, if this represents the distance, then I need to take into account this whole thing is 0.1, this part is, I guess, y, and so the distance will always be the total distance, take away the distance to the bottom, tells me the distance I have to move it. And so generally speaking, the distance will always be 0.1 minus y. Now that's the top of the container minus y, as opposed to the surface minus y, what I normally do in force. The volume, now I'm talking about the volume of each of these slices, not the volume of the whole container or the volume of all the fluid. I'm just talking about the volume of one little slice. What's the width of each slice? Constantly 0.08, always?
Yes.
Yes. What about the length of each slice? Always 0.06. And the height of each slice? dy. The limits of integration, are they from 0 to 0.05 or 0 to 0.1? Yeah, only 0 to 0.05, because that's where the work is being done. I'm not pumping the air out of the top. I'm just pumping where the fluid is, and the fluid is from 0 to 0.05, right? I don't really care so much about the answer. You can put that in your calculator. That's not an issue. Let's talk units. This was newtons per cubic meter. This was distance. What are the distance units? Meters. This is the width. What are the units there? This is the length. What are the meters there? Meters. And the height. What are the units of the height of the slices? Meters. Then you can see that 3 of the units of meters divide away, leaving you with Newton meters. Newton meters is joules. Your work units will be in joules. Thank you, Mr. McKellar. Nice. Nice to teach you. All right, so let's talk about a little more difficult, actually getting a little more difficult. We'll throw in some wrinkles in here. This half barrel, I guess you could say, is meant to be circular. I know it looks like it's stretched, so it's not semicircular sides, but they're supposed to be circular. When you get a circle, always put the center put the origin at the center of the circle. It's so much easier if you do. So I'm going to put my origin there, and because it's only a half circle, it'll be like that. Let's fill in some details. This edge on the coordinate plane, what is that edge? 4, -4. What's this y? -4. It says the fluid is a height of 2 meters. So that makes the height, or the water level, at -2 on the coordinate plane, right? And I guess this length, if I wanted to include it, is still 12 meters. You follow? Okay. Well, then here we go. We're finding the work that it would take to pump the fluid out and over a top edge or a hole in the top of the container. So, rho, distance, volume. What's the rho? 8,000 newtons per cubic meter. I am not picky about the units within the setup of your problem. This isn't science class. I'm fine with you leaving the units off the work until the end. The distance. The distance you have to pump each slice. What is it? 4 would be, if I said how much to pump this slice, it would have to be 4. But what about this one at -3? How far would you have to pump it to get it to the top? You have to pump it 3, right? So when the level was at -3 or the y was -3, we had to pump it 3. When the level was at -4, we had to pump it 4. So in general, the distance is -y. Or think of it as upper minus lower. The top edge is 0, the lower is y. It's always the opposite of the y. So you could go 0 minus y or -y is 4. Fine. In terms of the volume, again, remember, always remember that I am talking the volume of these sheets. I can't do just the volume of the figure itself. Each one has a different distance. So I'm talking about each slice's volume. That is, despite the circle, it's still rectangular prisms being pushed out. So it's still a length, width, and a height, or a width, length, and a height. I'm going to go in that order. What's the width of each of these slices? Constant or varying? X or 2x? 2x, okay. So 2x, I'll deal with that x in a minute. What about the length of each? Always 12 for every slice? Yes. And the height of each slice? dy. Okay. We'll get the limits of integration in a second. Let's go 8,000. You can definitely feel free to pull some constants out. So if you want to pull the 212 out, that's fine. I'm just going to leave them in. The x varies, obviously, because we've got an x there. But in each case, the x at any point relates to the y by virtue of being on the perimeter of that circle. So what's the equation of the circle? X squared plus y squared equals 16. So x is square root of 16 minus y squared. Don't worry about the plus or minus because really I'm just taking the positive side and doubling it. That's what 2 is. So we're cool. All right, dy, what are the limits of integration? -4 to -2. Only where the fluid is where I'm going to be doing any pumping. That by hand would be a little uglier. It's not, I mean, it's pretty nice use of, but you can use your calculator. The units would be joules on the homework. Right now, don't sweat it. But you would crank that out in your calculator on these and put the units on. Questions? All right. Let's pause for a second. You're going to start to see in the homework two-part problems. Find the force, find the work. It's important that you don't get the two confused. So let's pause and distinguish between the two. In force, it's row depth area, and depth is about the distance from the surface of the liquid to a slice. So it's fluid surface minus y. The area is a function of only the front face, not how far back. Not how far back. In most cases. The limits of integration are still where you're feeling force from the liquid, so they're fluid low to fluid high. Not container, I don't care. Now if you compare that to work, work is row distance, you're pumping a slice, volume. Distance will involve getting it to the top of the container. So it's more like container top minus y. Volume builds off the area. it'll take that front face into account, but also uses how far back. So a third dimension, really, it's area based times some height factor. The limits of integration are still fluid. I don't care about pumping the air out of the top, just the fluid. So they are the same for both problems. All right. So this, after reading this in the last class, this reads really badly. So what I intended was a triangular face with the top edge of 3, which is straightforward enough. The side I was referring to is 4, and the height 7. That to me is the height of the prism, which is the distance between the congruent figures. That's what I meant. All right. It's half filled with gasoline. So let's start with drawing the origin. On triangles, it's best to put the origin at the bottom of the triangle. So I'm going to put the origin here. I'm also going to flip so it's positive x's slash first quadrant. The force would be the same whether it was on the left or the right. That doesn't matter. So I absolutely can rewrite it that way. So I'm in first quadrant, which is always better to work with. Showing my dimensions here, this is 3. This is 4 to the top, but it's only half filled. Half filled. Not by volume, but by height. And the height, you can either draw this way or this way. It tends to look better if I go that way. So I go this way. So I'm going to put that a little lower. You with me? Okay, so let's compare and contrast. First, A is force. Force is rho, depth, area. Rho they give us. The depth. What's the depth of each side? Is it 2 minus y or 4 minus y? 2 minus y. How deep is relative to where the surface of the fluid is, not the top of the container. I don't care where the top of the container is. The area. The area is not the area of the triangle, but the area of each of these slices, which, taken thinly enough, are really just rectangles. What's the base of each of those rectangles? Constant or varying? Varying. X or 2x? X. Height is dy. So 2 minus y. So what is x then in y terms? Because I'm integrating with respect to y, I need to put x in y terms. I can't integrate x with respect to y. Actually, you can, but that's count 3. So what's the relationship between any x and any y at any point? Three, four, so 4. Oh, you might already be one step ahead of me. What's the original line before inverting? What's the slope of the line? Y equals 4/3 x. So x, which we solve for, would be 3/4 y. Okay? So x is 3/4 y. Limits of integration? 0 to 2. And the units on that would be joules? Newtons. Okay. B, work. Work is rho, distance, volume. Rho is still 6,600. What's the distance you will have to pump each slice to get it out over the top edge? 4 minus y. The volume, how will it be like the area? How will it be different? Times the height, or whatever you want to call this. I called it height of the prism, but really it's how far back it goes. So it's like the area, 3/4 y dy times an extra, though, 7 at this point then for work, I care about how much volume there is to move. I need that 7 in there. Limits, are they still from 0 to 2, or do they change 0 to 4? 0 to 2 still. And the units on that final answer would be? Okay. Try the last one to get you trying some on your own. Keep in mind, however, things will change a little once in a while. Most of the problems we do in the book are rectangular face kind of, or rectangular slice or sheets kind of problem. But many books throw in cylinder problems once in a while, so keep that in mind. As I said, you generally want to put the origin at the center of the circle. In terms of which circle here, why don't we put the origin at the center of the bottom circle, the barrel. Try force on your own, and we'll talk about it in a minute. Weight density of water is 9,800, by the way. We haven't got you here. Do you agree with the depth being 1 minus what? That's not really an issue. The area, what's the area that is feeling the force, given that it's not a flat front face, but that face goes all the way around? Yeah, if you look to unwrap it, the edge of the rectangle, it's still a rectangle feeling forces, but the edge is 2 pi r in the height dy. So, you might get for an area calculation something on the flavor of 2 pi. Is the radius constant or vary? Constant. You can see how a cone would be problematic. 0.4 is the radius, and the height is dy. From where to where? 0 to 1. Cool. Try work if you haven't already done so. We'll go over work in a minute. All right, so distance. 1 minus y or something else? 1 minus y. All right, the volume then. On the previous ones, the volume related directly to the area of the base. I just took the area of the base times the other dimension. I'm not quite sure if that's going to wash here because it's not so much a rectangular prism. What did you say for the volume of each little sheet? Yeah, it's a circle. You're talking about the volume of this little thin blue cylinder. Area of the base is pi r squared, and the height is dy. Let's see, 0.4. So this is one that doesn't really go directly off the previous. I didn't use the circumference for this. It's for the area, or the volume rather, of a cylinder. 0 to 1 still? Does that make sense? Okay. I can tell you today it's probably going okay. As days go on, people start to bleed into each other and get mixed up. So that'll be an issue you'll have to fight. Questions on 76. I imagine 10 might be a question, if I'm not mistaken. It was the derivative of the sine of x degrees, probably. I meant for that to be orange degrees. Any other questions besides 10? 20 or 22? 22. Okie dokie. What? 18. Cool. All right, I'll be happy to add questions to that. But I don't know if you remember way back, it's set 25, 6, or 7. You were introduced to the idea of the derivative of sine. And remember, back in the day, that I tried to get that idea across by having you draw tangent lines. So if you were to draw sine in radians, I asked you to figure out what will the derivative be by drawing tangent slopes. So if you're in radians, then the scale of those numbers isn't so large. Pi over 2 is ugly for sure, but it's pretty small scale numbers, like 1.5-ish. So when you laid a grid on this, it was actually fairly easy to see that the slope, when it was on grid paper, was pretty close to 1. So that when you graphed the slopes, you said, okay, at 0 the slope is 1. And then at pi over 2, the slope is 0. And we talked about how that's how you came to figure out that the derivative of cosine of sine is cosine. Yeah? What I'm trying to get across here is that is only true if the trig is in radians. If I tell you, hey, you're in degrees, what's the derivative of sine? It's not cosine anymore. Okay, that's what I want to get across, at least not quite cosine. Imagine if I asked you to do this in degrees. This then would be 90 degrees. Instead of 1.5-ish, it would be 90 degrees. If you were to then look at what is the slope here, it's more like instead of up 1 over 1, it's more like slope is 1/50. So that if you were to record the slope here, it would be practically nothing. Here would still be 0, so that point would still be cool. This slope would be more like negative 1/50th, and this slope would be 0. So you kind of get cosine, but much smaller. Well then, the idea of all of our calculus that we do on trig functions is based on being in radians. That's largely why you study radians, not because they're just better anyway, but because all calculus is predicated on radians and the scale of the numbers being that small. If you were to use degrees, well, then all bets are off. That then means if you wanted the derivative of x degrees, you would first and foremost convert it to radians. What is x degrees in radians? What's a conversion from radians to degrees? All you need to know is a case of, well, give me an angle where you know both radians and degrees. Pi radians is 180 degrees. I would put 180 degrees on bottom, radians on top. So if I wanted to take the derivative of x degrees, it's actually, or sine of x degrees, it's actually the derivative of pi x over 180 radians. The derivative then would involve a little bit of a chain rule. It would still be cosine of pi x over 180, but by chain rule, then I take the derivative of the inside, which is pi over 180. Now that's roughly 150. The factor by which the slope is shrinking here. The point I'm trying to get across is this. All calculus derivatives and rules are basically being in radians. And if it's in degrees, then you're going to have to make changes. Understood? Good, good. Great. Let's go to 22. Question on 22. Oh, this was so cool. Didn't you think this was awesome? Oh, golly, it's so cool. Okay, so here's the deal. You've got this semicircle. Y equals the square root of r squared minus x squared. And if you revolve it about the x-axis, then what's made is a sphere. Right? We could find the volume, or actually develop the volume of that sphere. Isn't the volume of the revolution just pi times the radius squared? What's the dx of each slice? Or sorry, the slice height is dx or dy? dx. The radius is not the constant r of the problem, but the varying radius of the slices. And the radius is always the y, which replaced with its equation is that, yeah? What are the limits of integration, considering that it's x? What's this side and this side? Given that I don't even have an actual defined radius, it's just a general r. Well, this is r, and this is negative r. All right. Well, before I integrate, let's make my life easier. The square root and the square root cancel each other out, so it's just integrating r squared minus x squared. R is not a variable. This is a constant. R is a constant. So when I say integrate r squared, think integrating 5. What's the antiderivative of 5 with respect to x? 5x. So if I integrate r squared with respect to x, it's just r squared x. So the antiderivative is something like r squared x minus the antiderivative of x squared from negative r to r. When I put in r, I get r cubed minus 1/3 r cubed. When I put in negative r, I get negative r cubed plus 1/3 r cubed. You can either simplify inside the parentheses or combine the like terms. Which do you want to do? Simplify inside or combine like terms? I'll simplify inside. R cubed minus 1/3 r cubed is 2/3 r cubed. Negative r cubed plus 1/3 r cubed is negative 2/3 r cubed. Oh, 2/3 minus negative 2/3 is 4/3 pi r cubed. That is the volume of a sphere. All right. They also, yeah, isn't it? They also tell you, you can also do the same kind of process for the volume of an ellipsoid or just some cool things. Cone. At any rate, they also say, hey, there's some sphere that has a surface area of 16 pi square units. What's the volume, I guess? That is kind of like a geometry one or algebra 1 problem. If the surface area is 4 pi r squared, and that's equal to 16 pi, that implies that the radius is 2 or 4. 2. And therefore, the volume of 4/3 pi r cubed at an r of 2 is, what, 32 pi. Cool. That was a good problem. Fun. 18. Question on 18. Is that still a question? Integrate actually 2x. All right. Would this be better by taking no. All right. Normally I would say, can I clean it up somehow? And I guess you could take that greatest common factor. But it doesn't really, the algebra is kind of funky, so I think the intention is that you do this in 2 integrals. And both with very different approaches. This, integration by parts or USO? Ultraviolet voodoo or USO? Ultraviolet voodoo. Okay, so this is integration by parts. This, integration by parts or USO? That's USO. I think that should get you going. If you had that and you want to go more, I'm happy to go more. Okay. Cool. Let me know if you have questions. All right.